So before we even start, end of this presentation, irrespective of what we gain from this, at least we'll get an understanding or about learn a new language called as Racket. Okay, so Racket is a language which is written. Racket lang. If you want more information, you can go to the site. I'll just start presenting. Racket lang. Racket is fundamentally a dialect of Scheme, which is deriving from Lisp kind of languages. So this is and the IDE which is used for writing Racket is called as Dr. Racket. So Dr. Racket looks like this. I'm just going to fire up that IDE. Like, what are the different kind of IDEs we use? Eclipse, NetBeans, IntelliJ, yeah. Visual Studio, somebody? Anything else? Any other IDEs? Pardon? Qt Creator. I don't know what that's. Sorry. C++. Okay. We hardly program in C++ these days. Okay. And anything else? Any other IDE? You know? Android Studio. And what do we do for iPhone development? Xcode. Right. Multiple IDEs. So this is Dr. Racket. Okay. So Dr. Racket is the IDE which we use for writing Racket code. Okay. This about IDE, at least we'll have some grasp of what is this language about end of the session. But this session is not about this language. This language is just going to be used as a vehicle for us to learn something else. Right. So back to the presentation. Right. Okay. This is a quote by Richard Feynman. Anybody knows who's Richard Feynman? Yeah, he's a quantum physicist, right? Huh? I'm not audible. Okay. Anybody knows who's Richard Feynman? Yeah. Yeah, quantum engineering. Okay, basically he's a quantum physicist. He did some path-breaking research in quantum physics. So he tells about this. You can know the name of the bird in all languages of the world, but when you're finished, you'll know absolutely nothing whatever about the bird. So let's look at the bird and see what it's doing. That's what counts. I learned very early the difference between knowing the name of something and knowing something. This is the theme of our talk, which is going to be today. We just saw before in the radar, there are bazillion things in technologies which are coming up. There are multiple languages, multiple paradigms. There are so many things. But fundamentally, what everything does is computation. So instead of looking at multiple technologies and various platforms, it's important to understand what is that something. We can know sparrow in multiple languages, Kuruvi, Chidiya, or whatever we can call a sparrow in a number of languages. But fundamentally, a sparrow is a sparrow, and it has got certain characteristics. So once we know about that, we can reason about sparrow in a better way. So that's what we are trying to do today. So the topic of this, understanding programming language design by writing a simple programming language. That's what we've got to understand a language, how a language is actually constructed, and for us to reason about a language which we use day to day, we're going to write a small language. So I'm Vignesh. I blog at tintinprogrammer.com. This is my email ID and this is my Twitter handle. So I'm speaking after almost 10-12 years. Last did public speaking way back in 2004 or 5. So doing after a very long time. So please, bear with me for any glitches and little rustiness. And please feel free to write back to me of any feedback which you feel like. Right. So I am a native of Coimbatore. So I did my schooling in Bharatiya Vidya Bhavan, passed out in 2002, and went to Pilani for my graduation. So after that, worked for some time in Aditi Technologies in Bangalore in the early days. And after Aditi, moved to SAP Labs in Bangalore. So after SAP, went back to Make My Trip in Delhi, NCR. After Make My Trip, worked for education software called as Infinity in Noida. So after that, came back to Coimbatore around 2012-13 time. So it's about currently I work for a content management system firm based out in RS-Puram. It's an Australian firm. It's called Incom CMS. Okay, why? There are two reasons why I had to choose this talk to speak. To understand the motivation, because once we understand the motivation why we should be hearing this, it makes us to actually digest the content more nicely. So as a speaker, when I was thinking about this topic, the primary reason why I wanted to do this was I felt a great level of benefit by understanding these concepts. I've been programming, starting from 2002 or even earlier. We started in Tamil Nadu syllabus, we start programming, say, in 11th or 12th, during our days. So from that time onwards, I've been doing programming. But programming languages every time used to be, oh my God, I have to learn a new language. And it's quite a steep learning curve. And we spend a lot of time trying to understand what a language does. So this was me also till around 2012-13. So I came back to Coimbatore, and at the time I wanted to do a PhD. So to do a PhD, I was looking at taking various computer science courses to understand what is the area which I can actually focus upon. So one of the courses, couple of courses which I did was with a university and a couple of professors, and those professors taught me, I mean, during the course of that courses, I learned about this concepts of reasoning about programming languages. And once I learned about this, I feel very, very comfortable with the languages. I really not, I mean, out by any big languages which come up or any big frameworks, because it's a scientific way how you can actually reason about it. And as for the audience, what is the key takeaway that you're going to take back, going back to your desks? None of us are going to write a new programming language, right? That's not, that's for people in, say, Anders Hesselberg, or, I mean, what is the creator of Clojure? What is his name? Anybody remember? Huh? Creator of Clojure. I mean, these are language creators. There's a separate section of programmers who are actually language creators who go and write. Golang was written by Gillette Braca. I mean, the team of people. I mean, people over there. These kind of people are different kind of programmers who actually create languages. Many of us, or 99.5% of us, do not fit into that category. We write application software using the languages which were designed by these people. So, but how is this talk going to help us? Is that when we go back and sit to our desk and look at a program written in a language, we can reason about the language better. Once we can reason about the language better, we can reason about the program which we wrote in a better way. So that's the key takeaway for it. And another thing is that I would really love programmers to be abstractionists. Many of us, even, I mean, even when job ads goes out, even technology companies, they look for, okay, we want a Java programmer, we want a Scala programmer, we want a F# programmer, C# programmer. I mean, I feel this is very, very naive way of actually doing recruitment, because a programmer is an abstractionist. He doesn't look at the syntax. All these things are syntaxes. So this talk is going to not pour over the syntax, but understand the meaning or the thing which the syntax represents, right? So that's the key takeaway. So the agenda is going to be this. We're going to have a brief overview of the classification of languages, and we're going to understand what is the scientific design of languages, and we'll introduce a bit of Racket. So the way Racket is going to be, we are going to be learning the various constructs of Racket is in the lazy style. You know lazy languages? You know what is lazy languages? Lazy languages don't evaluate eagerly. So they don't, given an expression, a lazy language will not give a value immediately. Based on the, whenever it is needed, it evaluates. For example, IQ variable in .NET, well, I program a little bit in .NET for my living. So that's again a lazy construct. Unless you call .toList or some function, it doesn't actually evaluate. So similarly, we are going to follow a lazy style for understanding about the various constructs of Racket. And why laziness? Because we are going to write a new programming language, which is called as Mathil, and we are going to have 2-3 versions of it. One is V1, V2, and as we learn these new languages, what are constructs which we require to write, we learn that from Racket. And we'll also have a small talk about lexical versus dynamic scoping and a summary. And I don't know how much I'll be able to cover, but this is a wish list, is to expand our language further into version 3.0, which is to add, how many of us know here Lambda? Lambdas, yeah. Lambda X, which is Java, I mean 8 or 9? 8 is introducing Java, yeah. So we are going to trying to add Lambda to our language, and also Lambda along with the Lambda becomes Clojure. I mean, we add Clojure also to the language. And version 4 of the language is going to add let expressions. Anybody know what is a let expression? Like, and finally, we're going to see how we can add F# like pipe, syntactic sugar, to the language. Okay. So this is the thing. I'm not sure if you'll be able to cover these. Again, my point is not to complete the agenda, but I would really want each and every one of us present here to understand clearly what we are doing. Because for me, even if I cover 2 items of this, but we've understood that, it's going to be great. And also, I'm going to be a little bit, what do you call it, pedantic, or what do you call, how our teachers used to teach us when we were 2nd or 3rd grade, when we are taught the tables, like repeating the same thing again and again, because we are doing something very new, which we might not have ever done so far in our career so far. So I'm going to be a little more stressing the same thing and repeating the same thing again and again, so please bear with me. Okay, classification of languages. Can somebody from here, I mean any of us, I mean there are a few of us here, tell various languages classification? Have you ever done language? Little louder. Object oriented, yeah. Yeah, great. I'll just put it here, it's fine. Let me write here. Object oriented, okay. Anything else? Procedural, yeah. Anything else? Data oriented. Example? Pardon me? JI. Oh, that's a language. I don't know. It's a language called JI. For a macha. R is a data language. Basically, if you look at R is a language which is focused only on data. Okay. R. Okay. Any other language? Any other classification of languages? Pardon me? Structural programming. Yeah, I could just put that inside procedural because it all sort of falls in the functional programming. Yeah. Okay. Structural. Okay. Data oriented. Functional. FP. Okay. Functional. I mean classification of language. Yeah, Scala is an example of that. But yeah. Okay. Any other classification? Domain-specific languages are written, yeah, that's a category, but that uses some other language, right? DSL is written using any of these common languages which we use, right? Any other classification we know of? Any other languages categories? No. Okay. Declarative. SQL. SQL is an example of declarative languages. It's a type of declaration, and we have scripting languages. Scripting. We do a lot of scripting languages. Where do you put, okay, JavaScript? Where does JavaScript come under this? We all use JavaScript, all of us? So where do we put JavaScript in? We have object-oriented, structural, procedural, data-oriented, functional, there are some more declarative and some more categories. Where do you put JavaScript under? Huh? It's a procedural, no, it need not be procedural as well. Okay, I mean, JavaScript is unique. I mean, what I'm trying to hint at is a language has cross-cutting concerns or cross-cutting features. It's not specific. JavaScript actually, I mean, truth to be spoken, is a functional language given in C's clothing. If you look, I mean, I think Crackpot's JavaScript good part, he explains about this. Fundamentally, it's a Lisp. What we're going to see, Racket, it's a Lispy kind of a language which is given a C clothing. So JavaScript, but a lot of people say JavaScript is object-oriented programming. Yes, it can. You can create JavaScript objects. Yeah. A lot of these frameworks, if you go Angular and all of that, they use JavaScript objects. I mean, they all call object-oriented JavaScript and so on. So this classification of languages is not the right way by which we can reason about a language. If you want to understand JavaScript, for example, if you approach it, okay, it's an object-oriented language, we'll never understand it properly. In a completely object-oriented kind of code which written using JavaScript, if we say, okay, JavaScript is a functional language, we'll never can reason about JavaScript properly. So what this kind of categorization of languages and reasoning about the languages is not a very prudent way how we can go about understanding any given language. So what is the problem? So let me go one step next. Present. Right. Okay. Who are these people? I'll come to the classification problem, why that's a problem, and by explaining this. Any idea who are these people? Pardon me? Not Shakespeare. Alan Turing? No, not Alan Turing. Go back to our biology and chemistry classes. Huh? Charles Babbage? No, it's not Charles. It's nothing to do with computer science. These are pure scientists. Okay, so not for the sake of time, let's further. Okay, this guy is called as Carl Linnaeus. Who's Carl Linnaeus? If you think of 6th standard or 7th standard biology, binomial classification of species, right? We have come across this. Vertebrae, invertebrate, mammalia, Pisces, and all these classifications. So this was this guy. Okay, this is his binomial classification, right? This is again, we remember to what earlier we saw, how we try to classify languages. So various kind of classifications, right? And this guy is called John Dalton. Everyone must have come across this. An atom is the most fundamental point which cannot, unit of substance which cannot be broken, or, I mean, we have heard of this. And he proposed this atomic model, and also he came up with this concept called as periodic table, right? So what did these two people and many more scientists do? So really think about it. It's very interesting what they did. What they did is, everything which we see in this room can be represented by the periodic elements in the periodic table. Every single thing, be it this laptop, be it this projector, be the, this table, anything which we see, the chair which we sit, the mobile phones which we use, are nothing but combinations of any of these elements. Correct? Agree? So what these guys did, I mean, especially Dalton, and also any living being, for example, Linnaeus, the classification was this. He any living species, any living being in this planet Earth, you can put in one of the boxes which Carl Linnaeus created. That was his classification. So what these guys did was they took a complex system and broke down that into fundamental pieces about which we can reason about in an unambiguous manner. That was their major contribution. Big system. Imagine, I mean, reasoning about the whole world without these few elements which I got. So right now we can, with chemical equations, we can represent any complex substance. Polythene. Polythene can be written as a complex. I mean, I don't know what ring it is, but we can express polythene as a using a proper chemical equation. And what is that chemical equation? It has got carbon, it has got oxygen, it has got few other elements. So these people, the principle which they did is they broke down a big thing into a small thing about which we can reason about in an unambiguous manner. Second, they gave rules of composition, how these small things can actually compose to form a bigger thing. And their classification was very fundamental. For example, spices, let's say fish. A species called as fish, everything in the fish category can fall under the fish. Anything which can swim in water, which has got fins or which has got certain characteristics, can be classified as a fish. No ambiguity. So inert gases, any gas which will never actually combine with any other element are called as inert gases. It's unambiguous. You can clearly reason about it, right? So this is their main contribution. Second, I mean, last one, we all know this, A, B, C, D, Z. Every language which we speak, every sentence which we write is nothing but a composition of these 26 alphabets. So for us to take a big Shakespeare book and to understand about, okay, let me understand what is the rules of grammar and all that, it's going to become very difficult because you're looking at a large book and it's not easy to reason about it. So similarly is our case with languages. We have a very, very large language. So we are going to come back. So with this theory of understanding of classification, we'll tell you why the problem is of classification of languages earlier, which we did is wrong. Because we don't have a core fundamental unambiguous definition of something. When we look at languages, we cannot, for us to classify something as something, we require to be able to unambiguously define something. But in terms of languages, we simply cannot define it. Let's say object-oriented language. When we take object-oriented language, okay, objects, it's got to deal with objects, but what is an object? What is the representation of an object, right? JavaScript, if you run JavaScript, object is nothing but a hash map, right? There's nothing like an, yeah, it's a, yeah, associate? Array, yeah, it's just a, yeah, or it's an array. Fundamentally, JavaScript is array. We don't have anything called as an object. Whereas if you take Java or C# object means something else. Object is not an array. So when you take even object-oriented programming, we don't have agreement. Okay, I can reason about that in a particular way. In as much as we have agreement about inert gases, in as much as we have agreement about, say, a classification of species. So that kind of a classification is not a right approach to reason about languages. But that doesn't mean that it's wrong. What that blocks is that the style of programming. For example, we can write a perfectly functional program in C# or Java. Whereas using a functional language like Scala, we can write a perfectly imperative code, which can be like object-oriented or a code which is not functional. So languages have a subset of various features which can be put in those boxes, but languages in themselves can't be reasoned about in terms of those boxes. For us to reason about languages, we have to understand the core concepts. What does make up what is a language made up of? Any given big language has got a lot of constructs, but these constructs are nothing but a small, a big sugar. Heard of this term called a syntactic sugar? So every language has got a lot of syntactic sugars. If you really remove all the sugars out, all you got is a core small language about which we can reason about very easily. So once we understand these small concepts, we can easily understand the bigger concepts. For example, C#. I program primarily in .NET. So C#5 introduced a feature called as async and await, which is really awesome. So async and await helps us to really do asynchronous. It's not asynchronous web programming, it's asynchronous server side, wherein the concurrent model, the execution thread doesn't have to wait for it's not about responsiveness, but it's more about scalability, where a single thread doesn't have to wait and serve individual requests. It can just spawn off some task, it can keep on going. And the C# system, the .NET systems takes care of everything. So it's a surface syntax. What is underneath it? It is nothing but this. That particular async and await block is actually desugared, or rather translated like this as a state machine. A state machine which takes various continuations as, and it passes the CPS. It's called continuation passing style, where the various continuations are passed back and forth based on the various states, right? So this is thanks to John Skeet. So if you would like to, you can always look up to John Skeet's blog to understand what is this about. Okay, basic racket syntax. So what we're going to be doing is we're going to write a small language with some basic fundamental constructs. Okay, this is not, I mean, I'm not going to be speaking about compilers or the how you realize a language in the more operating system level, but this is more about us to reason at a language at our level where we, the kind of languages which we interact day to day. It's more aimed at that. Right? So racket. So let's get back to our racket. This is Dr. Racket. So Dr. Racket has got two parts. One is the top window is called as a definition window, and the bottom window is called as an execution window. I mean, it's like a REPL where you can actually type things and execute it. I'll just show some basic things. This is how you start this is called as lang racket. So if anybody is not following the basic syntax, please do stop me. I can explain. So contrary to the languages which we know, for instance, this is a list style of doing it. We reason from left to right. Has anybody worked in Clojure? Clojure? So Clojure has this kind of a syntax. I mean, Prakash might have come across Clojure, right?
Yeah, but not OScript.
Oh yeah. So Clojure kind of, this is a Lispy kind of syntax where you start from the left. When you want to add two numbers, you do plus this one. For example, here you do plus 5, 6. It returns 11. So it's a REPL, readable print loop. Okay, is this? We should increase the font. Okay, right. And the basic evaluation from left to right. And how do you define function? This is how you define a function. Like you define the keyword define follows keyword define, and this is how. This is not actually. This is like what do you call it? Define x, square x. Okay, define x of 5. So this is how you define a language. Basically, you're assigning a value to a variable. That's how you do this. Define x of 5. Constant x. Define this. Is how you define a function. So, whatever. Oh, cannot redefine because I've already run this with the language above, so the environment already has it. I can just look up for x and get 5, and I already defined this function square, which is x into x. So you could just call this function. You call by opening a parenthesis, and you give the name of the function, and you pass a value. You get 25 back. So this is the basic syntax of racket. So this is functions. I'll just go show one or more constructs which is going to help us to understand our language. This third construct is called as a struct. Struct basically helps us to define types. Okay, so we got a struct. We define here struct 3D point xyz. So it's basically a type which has got three, place where we can take 3 parameters x, y, and z, and you can construct, so to say, an instance of that struct using this way. Define A. We give 2D point of 5, 10, or define B 3D point of 1, 0, 10. And how do you get values out of a thing? For example, 3D point of x, and you pass the instance which is B, so you get the value here. If you want to give 3D point of Z. This is some basic syntax about racket. Okay. And I'll do a little bit more about conditionals. I'll come back to this. So how do you look up check for conditionals, booleans? So hash t represents a boolean value, and hash f represents a boolean value true. The hash f represents a boolean value false. So you can always check if, for example, the string, if it's a number or not, which is using this predicate. So this anything which is followed by a question mark sort of is a predicate by convention in racket. Whether you can check for this. This is again booleans, and next comes conditionals. Conditionals again is a con construct. So a con construct fundamentally takes, for example, here this is the construct. What it does is, this is a con, again we reason from left to right, and this is the expression which basically evaluates into whether this is a conditional, and based on the conditional, if it is true, it does something, and if it's false, it comes to the next conditional and executes. So when it is hash t, it is true for everything. Okay. So this is the conditional, and this is the again defining a conditional. Conditional takes this, it checks for the condition. If it's true, expression 1 is executed. If not, it goes to the next one. So these are some basic constructs which we are introducing in Racket to write our simple language. Okay, so I'm going to be, I think it's already 8:20, trying to wrap it up as soon as I can, but Yeah, sure. Yeah, because I've got, this is just the version 1 of the language, and this is something really, what we're doing is first time we are all doing this, and it's going to really help us to reason about languages in a better way. Okay, now we are writing a language. Put yourself in a hat of, say, you are the creator of JavaScript, or you are creator of some language you are creating for the entire world to use. There are going to be business systems written in the language which you're going to be creating, right? So let's wear that hat and reason about this. It's a language specification. We want, as we saw earlier, the process of designing a language. We design core constructs of a language, and we can wrap multiple sugars on it to expose, so in various ways, right? So let us, these are the requirements, specifications. Somebody has, any language, our domain is mathematics. Our language is going to be primarily used by math people to do some math operations. Okay, we want language specification, simple core language to do some math operations. Basic math are addition, multiplication, subtraction, and division. Okay, so I'm going to not use this. Let's say, for any mathematical operation. Oh, that process. Oh, where is that? Yeah. Our language should be doing this: plus 5, 6 is addition, multiplication of 5, 6, which is 30, and say subtraction of 10, 5, which is going to give 5, and division of 10, 2, which is going to give us 5. Okay, these are some basic operations which we want to encode in our language. Okay, to do this, let's say we are going to write a language. What are the basic things which we need? We're going to create a language. So to do these basic operations, what are the things which we need? Yeah? Huh? Methods, okay, right. Furthermore, in a more fundamental level, what is the fundamental element, the basic unit of this programming language is going to be? No, this is we are not doing that. Compiling our syntax to machine understandable. Yeah, this is the machine understandable code. This is plus 5, 6. So again, algorithm. Okay, I'll tell. Do we need numbers? Without numbers, this is all about mathematics. So we require to have numbers, but we cannot use this number. We are writing a language, so we require it to represent the real world number in our language. Right? You're creating your own new vocabulary, right? In Tamil, Tamil R to E is there, or Sanskrit R to E is there. So like that, we are creating our own vocabulary. So our vocabulary has to represent this real world thing in our terms, right? Let's define that. So that is going to be a struct which is going to be called as num. This is num. So this is the representation of number in our language, right? So let's just do a basic so the strategy I'm going to be using to realize this language is going to be one of interpreter, right? Interpreter is, again, that's a difference. Okay, before I go into this is our simple mathematical expression. Okay, verify. Oh, yeah, this is again tax finding common define. Okay. It's a simple mathematical expression. We have written our first small interpreter, which would again take our language and give a value. Again, compiler is something which will translate a language into another language. That's what we are telling. Compiler is something which will translate something. It will take a program in a particular language and it will give another program in another language. And that again would be taken up by another system. For example, JVM, we are speaking about JVM CLR. JVM CLR are what do you call? We have a compiler, C# compiler, Java compiler, but the class file which gets generated is executed by the JVM. And JVM is an executor, and it is that executor which actually produces values. The compiler just produces another program which is of not of much value unless somebody actually executes that program. So we are using an interpreter, which is nothing but an evaluator, which produces a value to reason about this language, right? So this is our first interpreter. Interpreter is what? This REPL. If you look at Chrome, if I think most of us use this developer tool. So you look at this small arrow here, the REPL. So this REPL is nothing but it can take values. It takes 5, it gives us 5. It takes 5 plus 6, gives us 11. So what we are trying to achieve here is this REPL. We are writing this REPL, which will take any expression and give us a value, right? That's what we are trying to do. Right now, this is evaluate is a REPL. This is the same bracket syntax. How do you invoke a function? You call evaluate, and what do you pass in? We have to pass in values. What does this interpreter? What values can it take? Numeric values. Yeah, let's try. Okay, 1 second. Before that, I'll do one thing more. Do some more count expression here, and count is fine. Okay, let's do evaluate. Let's take 5. Ours is a mathematical language, right? We get an error because our language does not know what is number 5. We are writing a new vocabulary. In that vocabulary, 5 has no place. 5 has to be represented in a particular way. For example, let's in this case, in this JavaScript REPL, this 5. Okay. I mean, who tells this is number 5? This could be, I mean, the JavaScript vocabulary, it should understand this 5. For example, if I write FIVE, it's a string 5. It is not actually the number 5. If I want, I can write a language which can take addition of 2 5s and give a 10 of string. A 5 plus 5 in JavaScript would not give you 10, but it's about how we define your language vocabulary. So we are defining a vocabulary here which does not take 5. So what does it take? It takes evaluate num 5. So again, this is very important to get it right, because we are not using the same numbers which we know till now. We are actually creating a language which represents the real world numbers which the computer understands in a particular format, which our interpreter understands. So that is a concept which we have to internalize. Okay, we have done this. Next, we have this addition operation. We have to define addition. For that, we define a struct, which is again addition type. Okay, and addition requires 2 things. Plus operand requires, plus takes 2 operands, left and right. So for addition to happen in our language, we require 2 parts to it, right? So what does addition require in both places? Numeric values, right? But let's do that. Numeric values. We have to again branch on the type. I'll just copy paste for quickness sake. Okay, let's not do that. Add math expression. Add left part. Again, so I pull out a value from a struct. Okay. Plus right part, again math expression, right? So we got addition in. We have coded up addition. So imagine, again, this is how a JavaScript or any other language would encode its plus operator. When plus is, somebody is defining plus. In that language, plus means nothing. So plus would automatically be translated as underlying operating system would have some meaning for what is plus, or the underlying assembly level language will have something for plus. Plus means do this, add. If you've done 8085 programming, it's basically add operations. That's a chipset instruction which gets translated further. So somebody, when we are defining the language, have to define plus means, okay, do this. So we are doing the same thing here. We are defining plus addition through this way. Add math expression, add left part, which is the left part of the addition, and take the right part and add these 2 things. Okay. So I've got some tests running. Let's see. Let's have to keep this test consistently passing. Evaluate, add num5, num10. So add is undefined. I will not run this. So we again have a problem. What do you think is the problem here? Setting contract violation, expected number given num5. Yeah, tell me. Okay, but let's do that. Sorry, come here. Let me give 5 here. Okay, let's see if this works out. I doubt it, but 10. Add, okay, 15. Add 5 comma 10, 15. So plus add left part. This is fine. This sort of works, right? But let's see. This works. Okay. What about, can this be having only this part? Why can't it be add another 5 comma 7? Okay, this. Is that all right? It can have sub expressions, right? A language can have sub expressions. It may not be just this, right? Now what happens? We are again contract violation. Yeah, it has to be evaluated. Why it has to be evaluated? It has to be further evaluated. Yeah, it should be evaluated. Reason is, see here, this plus here, plus knows to operate only on numbers, which is Racket's numbers, right? Plus doesn't know to operate on our numbers. The representation of number 5 in our system is number 5. So Racket's plus doesn't know what to do about it. So do we have a program which converts this representation into numbers? Do we have a program which actually, that's what we wrote the first line, right? First line is nothing but it takes a num and returns you a integer, a Racket integer. So we actually have to call evaluate on this, right? You call evaluate on this, call evaluate, oh sorry, evaluate, and you evaluate the right expression, right? You do this, we do this. Now this will not work again. Why? Because when you're evaluating this 10 doesn't have any meaning. Previously we just pulled out this value from the language, but now this 10 does not know because we're evaluating it. When it again goes into the right part, it takes out 10 here, 10 from here, and goes into this evaluator. It type checks. Okay, is it num type? No. Is it first the left side will pass add 5 6 because it's a type of add. It will take two things and do the addition. But again, even within add is going to be a problem because again further it's going to come here and type check because that's again we recursively evaluated, right? So for us, when we are writing anything in our language, it has to be represented in the way the language understands. For example, if I write number 5 and number 6, 10, right? So it gives us 21. 5 plus 6, 11. 11 plus 10 is 21. So we return our simple language which takes addition. So multiplication case is going to be very similar to this. Just copy paste from here, which is going to just take these two expressions and add it. Sorry, multiply. Okay, here we are not allowed. Okay, unbound identifier. Okay, because we have not defined it here. So we have added addition, multiplication, these operations to our simple language. So what have we done here? We have trusted recursion, just recurred. Anything which you get, any complex sub-expression you get, because this left part of addition or multiplication could be a very complex addition expression, which is what we see in our languages. In our languages, we just don't write plus 3 comma 4. We can write a long expression of which our language will understand, which will be sort of understood by the language and it will evaluate to a value. So we're doing a similar thing here. So we've done these things, right? So let's again, another one language decision we are taking right now is, what is multiplication? Can multiplication be expressed in terms of addition? Yes, fundamentally it's addition. But we have taken a decision to add multiplication as a core construct. It's again a design process, design choice in our languages. For example, I was reading a blog sometime before where Eric Lippert, one of the C Sharp's compiler team, he was earlier present in Microsoft C Sharp compiler team. He was telling that particular language feature didn't make sense to us, so we didn't include that language feature. So certain languages add features later on, but not all the features are present at the right. I mean, you just keep iterating and keep adding. Some features they decide not to do it. For example, Java did not have lambdas till now. Java 8. I mean, it took very long time. I mean, I think Gilad Bracca or somebody, he told like the earlier drafts he actually proposed to use lambdas in Java, but it was not accepted. After C Sharp actually bought in this lambda expression and all that, it went in a very fast way. Java also has embraced this model. So it's a design decision which the Java language designers took at some point of time not to include certain constructs. So here we can take a design choice. Do we want to represent multiplication as a function of addition or not? It's again a design choice which we take and take a decision. For subtraction, we have taken a design choice like that. For example, though we have given a subtraction construct, subtraction could be fundamentally written as a syntax using addition and multiplication. Basically, this plus and minus of this. So we can we not have to actually have a separate construct for this. So again, these are some of the design choices which we take when we write a language. So this is a version 1 of the language which we have written so far. Written some tests, which is basically, I'll just run these tests, hopefully they should pass. Control-C. Okay, they pass. This is our first version of the language. So the important thing to understand is the communication or the us conversing in the terms of the language. Again, when we go back to our tests, when you look at a variable x, say in JavaScript, if you look at say var x equal to 5, understand x is something which the language, var is another keyword, just like how our interpreter we wrote add. So var is going to be understood by JavaScript runtime as a particular keyword in its system. It's not exactly the same, but you get an idea, right? So x is again going to be understood as something else, and phi is again like how we add our numval, it's going to be such kind of a value. So imagine when any error happens, okay, JavaScript is looking at this in this way, so let me try to reason about it in that direction. You'll be able to get at a problem solution faster. Okay, so this is first version of the language. I think I'm really running short of time and I don't know if we'll be able to do things. What I've done is there are various versions of the language, math2.racket. So what we do next is fundamentally adding functions to the language. We want to add functions. What we're going to be doing is say this define function, x is plus x10, define f some other function and call a function within it. So this is a basic feature of every language. So adding this to a language is a big step to support functions. So I don't think we have time, Selva, today. Yeah. So I don't know, maybe some other day it's good. I mean, this is version 2. If you look at the version 3, open recent, we're going to have one story so far as we have done version 3. When we go to version 3, we have done addition, multiplication, definitions, function applications, and environment. So can we have anonymous functions and lambdas? So you're going to expand the same language to actually have anonymous functions, lambdas, and to have higher order functions. Higher order functions are, I mean, you pass functions and you can return back functions. So our language is going to be built to support these higher order functions. And in the last, we're going to support, I mean, just math language 4. We're going to support this F# like syntax. For example, F# has this cool kind of syntax where, if I have it here, which yeah, this is a F# kind of a cool syntax where you just pass the pipe, this pipe forwarding thing. In Unix we have these pipes. You have a big thing, ls, grep, pipe, you grep something, you keep moving. So F# has this facility where a left output of the left goes to the next and goes this way. So it's 130. So we mature our language so that it can have such kind of a pipe operations using anonymous functions. And basically this is currying. Heard of this concept called as curried functions? Curried functions is nothing but a function which takes an argument, returns another function, which takes similar kind of the return type of the first function, and evaluates it. It's called as currying. So we add currying and all these features to our language slowly. But to understand this, it's going to take little. The professor who taught me, to the course who attended, he told in the class that you might have in your day-to-day job, you might write 100, 200, 300 lines of code. But for this course, the assignments, you're going to write at least just 30, 40, or 80 lines of code. But for that, you might have to spend hours and hours thinking about it. That's what language designers do. Because when you design a language, you're transcending the boundary of our human domain to the domain of computers. When you write a healthcare system, we think in terms of healthcare. When you write a system for air tickets, we think in terms of air tickets. But right now, when you write a language, you're not thinking in terms of any domain which we have experience of. We are transcending it in the computer's domain, how a computer will actually reason about it, and what kind of experience we can give to the user who is going to be using our languages, right? So it's a very, a beautiful exercise and really mind-bending. Not, I won't say too much mind-bending, but good amount of mind-bending to actually go through that. Writing a function, I'm not going to go much into that, but writing a function is itself a very interesting part, because you're going to have two parts. I'll just tell this concept and finish off. I'm not going to the implementation of it. There's something called as this, let's go back to JavaScript. Let's say function, sqr1, okay, x, what does it do? Return x star x. Sorry if it's, okay. This is a simple JavaScript function. They spell it wrong. function, okay, function sqr1. So this is a simple function. And how do you invoke this? sqr1 of say 5. It's very simple. This is going to give us 25. So there are two aspects to this function. Okay, what we have defined here, this part is called as a function definition. We all know it. We do use it day to day. But what is technically, think yourself as a language designer. You're writing this interpreter and you're coming across this kind of a syntax. So how do you make sense of the syntax tree? How do you form your AST? Is basically you understand this as a function definition. You give it a type or whatever you want, and when you call this is called as a function invocation or function application, where you apply a function based on it. So when we write our language, we have to have separate constructs for it. One is called as a funcdef, which is going to take three parts: function name, the param which is going to be passed. For example, the function sqr1 becomes a name, and x is the param which is going to be passed. And the body of the function return x becomes the body of the function, and the word function is represented by this type funcdef. And there is another one thing which we will bring in called as identifier, because somebody has to tell our language what this x means. And when we are evaluating, we also have to have this concept called as environment. The environment is the place where all these values can be looked up, because x has this, somebody has to substitute this 5 to x when it is actually evaluated in the body. So that again is a thing how the environment is there, and it could have nested functions. I could return another, if I define another function, that again I can call it, and the environment is going to become bigger. And how do we keep track of all the environmental, the parameters everywhere and to apply the right way? That's again a beautiful exercise to do. Right. So this is again, at least end of this. There are two things whenever we look at our systems. There's function definitions in the language in parlance. There's something called as a function application. Right. So this F# thing, this is a function definition, and this pipe is nothing but which applies the left value to the function definition on the right. So this is again the same thing. The thing is function definition, thing is function application. It is represented by various syntaxes, various symbols across languages. Once we know this basic concept of definition and application, we can reason about all our programs in a more better way. And more so when we realize this, we'll understand how closures work, we understand what is the lexical scoping, what's the difference between this and that, and all that. Maybe for some other day, but certainly I'd like to end here. It's at 8:40 already. Thank you so much for the patient listening. I'm just not even halfway through my talk, not even halfway, 25% of what I wanted to cover, but that's about it. Thank you. Maybe somebody is interested, we can speak to me later. And last but not the least, I just want to give the credits, which is very important. This is the credits. This is the best part of any presentation, where this is a couple of professors whom I really owe a lot, because this is Professor Sriram Krishnamurthy. I did a MOOC under him. It was not a traditional MOOC which we see in Coursera or edX or something. It was a course which we co-studied under with Brown students, which was really awesome. And though I was doing my other parallel courses, so I couldn't do as much justice to that course. I just did audit and basic quizzes. But whatever little bit I learned was really nice. Look him up. And the other one is Professor Dan Grossman. So if anybody has done a Coursera course called as Programming Languages, might have encountered him. So that again is a beautiful course, pretty mind-bending course, where we actually ended up writing a language like this as part of the course. So really credits to them. Whatever I have spoken, if it had even added 1% of value, all credits to these people. Right? And also would like to thank other couple of few more people is Joe Gibbs Pollitt, who was actually a PhD student under Professor Krishnamurthy when he was teaching that course, and they all ended up writing a Python's. I mean, they desugared the whole Python language in Racket. It was called as Pirate. So you can just Google it. It's called as Pyret. It's a nice language, giving a clear semantics of what is the Python, because Python is a BDFL language. You know what is a BDFL language? It's I mean, there's a one benevolent dictator for like the creator of Python. So he actually decides some features, which to go, which not to go, and only he gives direction to the language. But somehow there is no clear, well-defined semantics of what a certain thing means in Python. So these people did the research on that, and they wrote and they published in a conference. And other one, my friend is not friend, he's a senior person, is Ramakrishnan Muthukrishnan. He blogs here. He also was very helpful for me. And Professor Sanjeev Agarwal from BITS Pilani Goa campus, who also was sort of helping me and guiding me when he was looking for my thesis topics. And last, my good friend Ankur Dama. He was my friend who actually, different people taught me different things. Somebody taught me web, somebody taught me REST, somebody taught me databases. So he introduced me to the world of functional programming, which sort of made my intelligence peak to understand furthermore about languages, and which has led me to sort of present here. So these are some people I'd like to thank about. So yeah, we end with this. You can know about the name of the bird, many different languages. We can have various syntaxes, various big languages, but the core of the language is so small. What we defined. That's how a language design starts. The core is very small, and you realize once you understand the core very nicely. If we have got time to do the functions and function applications, we can understand, okay, this is what happens in a language when a function is defined, when a function is actually evaluated. It may not be the exact thing, but at least we'll get an idea as to what goes on. Because real term, the optimization and will be very, very high as compared to the simple things how we are implementing here. Right? Thank you. Thank you so much for patience. Thank you, Satish. Thank you, Silva.